In section 3.5, we're going to look at linear programming. So linear programming is when we're trying to maximize or minimize something to find an optimal value or a minimal value. So an example of this is maybe I want to optimize how much money a business is making, give it some certain constraints. Now a constraint, obviously in a business, you can't make infinitely many products and you can't pay infinitely many workers because that would eat into your profit. So when you talk about labor hours and cost of materials and all these different things, these are all what we consider to be constraints. So constraints typically are going to be a set of inequalities that will bound the possible solutions. So we have these different inequalities and they are going to bound the possible solutions. So for example, I might have a set of inequalities that says something like this: x greater than or equal to 0. Well, if this is one of my constraints, I can never use a negative x. Maybe I say y is greater than or equal to 1. I can never use a y that's under 1. So you can consider this maybe x is the number of hours of a certain position. I can't obviously schedule a negative number of hours. Maybe 1 is another type of position, and I always have to have one person working in a business or something like that. Then there can be combinations, maybe x plus y less than or equal to 10. 2x minus 4y greater than or equal to 20. You can have as many constraints as you want. So you have these constraints. Mathematically, they're just equations, but when you start doing these in word problems and stuff, hopefully these actually mean something, right? It's something to do with your business or whatever the scenario is that we're looking at. So when you have all these inequalities, obviously I could graph all these as kind of a system of inequalities, and that's going to form the feasible region. So the feasible region is just going to be the intersection of all of the constraint inequalities. So it's where basically they all intersect. So where do all these constraint inequalities intersect? So sometimes we'll have something like this. Let's say I have one constraint is x greater than 0. Well, here's x and here's greater than 0. And then maybe I have y greater than 0, so that's up here, right? So right now you can kind of see where there's an intersection of these two. And let's say I have a third inequality. Let's say it's a line that goes like this, and it's less than. So you're trying to find a region where they all intersect. This is called the feasible region. In this made-up example, you can kind of see there's this triangle that I have, and this triangle has the intersection of all of these inequalities. Now, this is quite a task to do by hand, but we're going to use the aid of the graphing calculators eventually to try to help us to find these feasible regions. Now, the most important thing in this feasible region, so there are all these points in this region, right? There are all these possible points. And then there are also these corners of this region, right? So these corners are what we call vertices. So the vertices are simply just the corners of the feasible region. So all these corners we call the vertices, okay? Now the vertices are really, really important. They're really, really important in linear programming, actually the most important points. You can ignore every point eventually except for those corners. So all these infinitely many points in here, we don't care about. Really the vertices, in this case it's a triangle, so there are 3 vertices. These are the most important points. Now these are the most important ones because these are going to be the ones that will maximize or minimize my function. So when we maximize and minimize a function, we're trying to make a function, and these are separate from the constraints, right? These are not going to be constraint things. there's going to be another function we're trying to maximize or minimize, right? We're going to make a function as large or as small as we can. So if it's profit, we'd like it to be really large. If it's cost, we would like cost to be as small as it possibly could. You see this a lot in construction where you're trying to maximize or minimize area based on a set of parameters. So you have so much building material, and based on this building material, I want to maximize or minimize some kind of region. So these are kind of problems we're going to do. So we'll have these constraints, we'll graph them, we'll make this nice intersecting region, we'll get the corners we call vertices, and then we're going to try to use those to maximize or minimize the function. Now the last thing we have is really the cool thing about this is the maximizing and minimizing always happen at the vertices. So this always happens at a vertex. So this is kind of a crazy thing to think about, and this is kind of the key of linear programming. I have that feasible region of all these possible combinations of x and y, whatever they represent. But the only ones that can maximize my function or minimize my function happen at the corners, at these vertices. So of all the infinitely many points, so in this little triangle region, there are infinitely many values. Of all those infinitely many values, only those three will make my function as big or as small as it could possibly be. This is the key to linear programming. So we'll look at a couple examples of kind of very mathy examples today. And then in class, we'll look at some more ones where we can actually take this and actually use it in some different word problem scenarios. So let's look at this example. We have graph the following system of linear inequalities. Name the coordinates of the vertices of the feasible region. Find the maximum and minimum values of the function. So these are my constraint. I have three constraint equations. X has to be less than 5, y has to be less than or equal to 4, and x plus y has to be greater than 2. So these are my constraints. And then I also have this function. In this case, I wrote f of xy. This is what I want to maximize or minimize. I want to make this as big or as small as possible over these set of constraints. Like I can't put an x of 10 in this function because x is less than or equal to 5. I can't put a y of 8 in there because y has to be less than or equal to 4. So over these constraints, of all the x's and y's that are valid for these constraints, which one makes the function the biggest or the smallest? So I'm simply going to graph these three functions. The first one is x less than 5. Well, x equal to 5 is just a big vertical line like this. And you can kind of just sketch it to the left. So these are all the x's that are less than 5. And if you type this in Desmos, if you type x less than 5, less than equal 5, pardon me, you'll get this graph, okay? Now I would do them one at a time in Desmos or by hand so you can kind of start seeing what happens with each one. So y less than or equal to 4, here's 4. Y is a horizontal line. So less than 4 is going to be down here. So right away you can kind of see where they overlap. They overlap in this kind of weird rectangular region right here. So right now I can ignore everything that does not intersect these two. Right now technically this goes on, it's always less than this, right? But right now only in this region are they both shaded. Now so I got this one done, I got this one done. Now my last one is x plus y greater than or equal to 2. So like we did last week, let's go ahead and get y by itself. So y greater than or equal to negative x plus 2. So I'm going to start at 2, and my slope is going to go down 1 over 1, down 1 over 1. So it is going to look something like this. Now, this one is greater than, so greater than is above. So if I go greater than, you can kind of see it looks like this. So if you look at the only area where all three colors are kind of shaded, my feasible region is going to be this area right here. It's this triangle. This is my feasible region. Now, the key is I have to find the corners of this region, right? The corners are going to be very important, these vertices. Some of them will be easier than others to find. Your graphing calculator will also obviously be very helpful in this. This one's 5, 4. This one over here intersects at -2, 5. And again, or -2, 4, pardon me. I'm just looking at the ordered pairs. And this one down here, this one's a little harder to see. I know it's at an x of 5 and it intersects the slanted line. So it's going to be 5, -3. Now, if you can't see it, Desmos, well, obviously you can click on it. But if I didn't know, I know y equals -5 plus 2 because it's the slanted line, which is -3. So I've graphed these three inequalities, and I found the corners. Now, the max and min of my new function is going to happen at one of those corners. So to find it, I just plug them in. So I'll just plug into the function -2 and 4. So I'll plug in -2 for x, 4 for y, and see what I get. So 3 times x is 3 times -2 minus 2 times 4. That's -6 minus 8. That's -14. And I'll just do this for each one of those three corners. I'll do the same thing for the next point. So let's say I do 5, 4. So 3 times 5 minus 2 times 4 is 15 minus 8, which is 7. And then finally, f of 5, -3 is going to be 3 times 5 minus 2 times -3, which is 15 plus 6, which is 21. So if you look at these values, I have -14, 7, and 21. So the maximum value of the function is 21 at the ordered pair 5, -3, and the minimum is going to be -14, and that's going to occur at -2, 4. So literally any little point in this feasible region, any of these little points, if I plug every single point in, none of them will give me a bigger value than 21, and none of them will give me a smaller value than -14. So you only have to check these corners. I went ahead and put a screenshot up here of what this would look like on Desmos. You can kind of see what I put in to get the feasible region. These are just the inequalities that we talked about. And then over here, I graphed them, and you can kind of see that this triangle is the region that you have in common, and I literally just clicked on these intersecting points. You just click on this with your cursor, and it will give you those points. So don't be worried about graphing them too much. You can use this to get those points and then plug them into the function to see which one is the maximum and which one is the minimum. Let's look at one more example, and then we'll go ahead and I'll show you what it looks like in Desmos and everything like that. So this first one says x greater than 0. So these are my constraints: x greater than 0, y greater than 0, y less than or equal to 2x plus 4, 3x plus y less than or equal to 9. So x greater than 0, greater than or equal to 0 is just a vertical line, and it's going to be shaded to the right because these are x's that are greater. Now my second one says y greater than 0. So y of 0 is this, and greater will just be above. These are very common constraints where you want positive x and positive y. You don't want things to be negative. So if you do this as an application, of course that's going to be true because you don't want things to be negative. Now the next one, y less than or equal to 2x plus 4, is already in the right form. So since it's in that right form, we'll go ahead and start at 4, and we're going to go up 2 over 1, up 2 over 1, up 2 over 1. So it looks like this. Now it is less than, so less than that would be over here. So no real shape yet. So right now, let's just take a quick moment to see where we're at. So if you look at where we're at now, essentially our region would be something like this that goes on forever, right? Because that's where they intersect. Now we'd like it to be, we'd like where it's just one region, but we have one more line to do, so I think we'll be okay. So the last line is 3x plus y less than or equal 9. So if I subtract 3x, I get minus 3x plus 9. So we'll start at 9, down 3 over 1, down 3 over 1, down 3 over 1. So there's that line, and we're going to go underneath. And so underneath this one, so you can see that when you do this, we get that region in the middle with all 4 colors. So again, you can see with all these colors how it can be kind of tricky to see. But it's just going to be this little region right here. This is my feasible region. So there are 4 corners to this. There's this one, this one, this one, and this one. So this one appears to be 1, 6, I believe. This one's pretty simple. That's 0, 0. This one's 0, 4. And this one appears to be 3, 0, I believe. So those are the corners of my feasible region. Now, certainly you can check that. I have the Desmos on the next slide that we'll see, but it looks something like that. So now to find the maximum minimum values, we're going to go ahead and plug them into our function. Now this function in this case it's a different function. It's 2x plus y. This is the function I want to make biggest. So f of 0, 0 is 2 times 0 plus 0 is 0. F of 3, 0, and again, you can do them in any order you want. 2 times 3 plus 0 is 6. F of 0, 4, going to plug 0 in for x and 4 in for y. So that's 4. And then F of 1, 6 is going to be 2 times 1 plus 6, which is 2 plus 6, which is 8. So you get the corners, you plug them in this other function, and so the max value is 8, and that occurs at 1, 6. And the minimum value this function can take over this feasible region is 0, and that's going to occur at, where does that happen? 0, 0. So we graph it, we get the corners of the overlap, we plug them into the function, see which one's biggest, see which one's smallest. Now obviously when we start doing these with word problems, having to write these inequalities, it adds another kind of layer of the challenge. So the last thing I want to show you in this first part of this video, as you can see here, is kind of my graph on Desmos. I just put them all in just as you see. You can kind of see the region here, just like we got before. And I just clicked on those corners to get those points. So those corners are what I plug into the function to be able to see what the maximum value of the function is and what the minimum value of the function is. So this is just kind of the first part I wanted you to do on your own. The rest of the notes you have in your packet we will do together when you come back as we finish up and start getting into some of the applications of linear programming.